Today, I'll be taking you from code to copper, the idea being that AI is transitioning from an algorithmic race to a physical infrastructure and energy story. AI capability has kept climbing while the constraints are becoming power, high bandwidth memory, and data center build-out. So, welcome to Berry Talks Data, where I talk about all things data, AI, and things that caught my attention recently. The opinions shared here are my own and do not reflect the position of my employer. The inspiration and a lot of the ideas in this was sourced from this video. It's only 25 minutes long, and he does a better job than I will at explaining each factor in depth. I'll put the link below. To start us off, we can look at these four headline numbers. $30 billion, that is the combined annualized run rate revenue of the frontier labs. So we're talking OpenAI, Anthropic, XAI. In 2025, with Anthropic alone reportedly hitting over $47 billion in May 2026. Also bearing in mind that this is revenue, they're still spending much more on their training runs. When you look at 130.8 days, this is the post-2023 task horizon doubling time from METR's time horizon, which was last updated in January 2026. So this is down from the around 7-month doubling measured over between 2019 and 2024. 725 billion is the confirmed 2026 AI capex of the big five hyperscalers, so Amazon, Microsoft, Alphabet, Meta, Oracle. A 64% year-on-year increase. 1 to 2 gigawatts is Epoch's electricity requirement projection for a single frontier training run by 2028. On the top right here, Metaculus is a prediction market. The community over there has moved their strong AGI median from July 30, 2031 at the start of 2025 to November 2033 by mid-2026. The forecast got roughly 2 years further away over the course of just 1 year. The original shrinking of timelines was triggered by OpenAI's O1 and O3 reasoning models, driving a 2 to 5 year optimism. The reversal came as real-world bottlenecks reasserted themselves. The chart in the background, that's just to give you an idea rather than a real measured data set. To be clear, this is still not a settled consensus. There are many vocal experts that are still predicting an imminent intelligence explosion, and Metaculus forecasters still put around 25% chance on AGI by 2029 and around 50% by 2033. And now for some of those bottlenecks. First up, generalization failure. So post-training reinforcement learning works well in verifiable domains such as math and code, but it doesn't transfer to messy open-ended tasks, which seems to rule out this as being a plausible fast path to rapid capability gains. The continual learning gap is also known as digital amnesia, which refers to the fact that models can't update their weights from experience or use after training. So Dwarkesh Patel had a mid-2025 essay calling this a huge problem, which has garnered wide industry agreement, including from Ilya Sutskever. Inference has diminishing returns. More thinking time yields log linear gains rather than exponential. And reinforcement learning inefficiency. Toby Ord, one of the key sources for the 80,000 hours video, estimates that post-training reinforcement learning is around 1 million times as inefficient as traditional pre-training. However, Epoch AI pushes back against this estimate and puts reasoning to training versus the test to time split closer to 50-50. Some things to bear in mind. Traditional next token prediction gives instant cheap output, whereas inference time scaling, meaning thinking time, has the model explore multiple reasoning branches before giving you an answer. This burns large volumes of hidden internal tokens. Agentic workflows become a multiplier here and consume roughly between 5 and 30 times more tokens per task than a standard chatbot query. From an economic standpoint, per token prices have fallen sharply while the absolute amount of tokens per task has grown. So the cost burden is shifting from a unit pricing model onto more the volume of computation. So how is the AGI consensus looking? Optimists have extended their timelines. So Musk is saying 2027 to 2030. Altman is saying 2028 to 29, while some of the skeptics have shortened theirs from multiple decades down to years. Gary Marcus is a vocal skeptic, especially of LLMs, and has revised his position from 2040s or none down to between 8 and 15 years, so around 2035. He does call the 2029 option awfully unlikely, and he holds a public 10-to-1 bet that AI won't accomplish his specified AGI tasks by the end of 2027. Gary believes that the field is converging on his long-standing view that scaling alone is dead, and that neurosymbolic AI advances will be required for true AGI. Now, this is the strongest empirical evidence that progress hasn't stalled. METR, or Model Evaluation and Threat Research, an independent nonprofit, measures the 50% task completion time horizon, the human expert task length that a model can complete with 50% reliability. The doubling time shrank from around 7 months between 2019 and 2024, down to 4.3 months post-2023. So this has been confirmed in the latest time horizon update in January 2026. This metric is built on synthetic software, machine learning, and cybersecurity tasks scored algorithmically, and it measures task difficulty by human completion time and not by the AI's wall clock compute. Although there are 2 caveats here, only 5 of the 31 longest tasks have real human baselines and the rest are estimated. And METR warns that estimates above the 16 hours limit are unreliable due to task suite saturation. So the greater than 16-hour Claude Mythos figure is an upper bound uncertain. This is the actual METR chart in log scale with 50% success rate. You can find it on their website. And this is the same, so 50% success rate, but now we're looking at a linear scale. And finally, 80% completion rate, back on that log scale, and you can clearly see the improvements over time, with Mythos able to complete tasks just under 4 hours with an 80% success rate, which is pretty amazing. Now for some of the interesting economics. So solving the ARC AGI 1 challenge, which is one of the benchmarks, the cost has collapsed from around $4,500 a task by 03 in 2024, down to $11 a task with GPT 5.2 in December 2025. This has been confirmed by the ARC Prize Foundation, so it's about a 390 times reduction, although independent analysis attributes most of that drop to reduced parallel sampling. So O3's high compute run used 1,024 samples per task, whereas later runs are only using around 6. This means that it's not just a pure algorithmic efficiency breakthrough, but also of note, humans solve these tasks that are between 30 and 60 cents each. So AI still costs 10 to 100 times more than humans cost for the same task. At the same time, total token consumption keeps rising. So there's been 24 times growth predicted, up to 120 quadrillion tokens a month by 2030. This is what Goldman Sachs research is predicting. And they've also found that inference cost per token has been falling year on year, 60 to 70% per year. To take a bit of a look at the capital, so Frontier Labs act as demand aggregators, collecting enterprise revenue and passing it upstream to cloud and chip providers. OpenAI's 2025 audited financials have shed some additional light on this, so roughly $13 billion in revenue against $34 billion in costs, a net loss reported at $38.5 billion after adjustments. Same story, broken into 2 sides. So you've got the labs, hyper growth, but structurally unprofitable, capped by algorithm efficiency and running out of human-based training data. And on the right, the infrastructure, NVIDIA, TSMC, hyperscalers, 45% plus margins, monopoly pricing power, capped only by the physical limits like power and thermals. So right now, the winners are the ones pouring the concrete and forging the silicon. Now, let's talk about the scale of the build. So the big 5 hyperscalers are committing $725 billion in capex just for 2026. And that's a 64% jump year on year. Push out to 2030, and McKinsey has total global data center capex at around $6.7 trillion. And these training runs are getting pretty crazy. So Epoch reckons that 1 to 2 gigawatts per run by 2028 will be required, and over 4 gigawatts by 2030. There have been similar infrastructure booms in the past with 19th century railroads and 90s fiber. The point is that constraints are shifting. It's no longer just model quality, it's high bandwidth memory and raw electrical power. And for something closer to my home, Australia, on the left, data center consumption in the national electricity market, we're at roughly 4 terawatts today, so 4 terawatt hours today, so that's about 2% of the entire grid. The Australian Energy Market Operator, so AEMO, has that hitting 12 terawatt hours by 2030. That's 6% and climbing to around 34 terawatts or 12% of the grid by 2050. That's a 25% compound growth rate. On the right, where it's landing. So Victoria has 30 facilities in the pipeline at 9 gigawatts. That's around 3 medium-sized coal stations worth of load. And New South Wales is even bigger at 44 facilities and 11.4 gigawatts. AEMO is now forecasting data centers as their own standalone load category for the first time. They're starting to become a dominant driver of grid growth. Some estimates say that if firm 24/7 generation doesn't keep up, we're looking at wholesale price spikes north of 20% by 2035. And for something a bit more technical, please, anyone with more electrical savvy, correct me in the comments. Large data centers behave electrically as what's called an inverter-based load. So dynamically, they act a lot like a grid-scale battery or a solar farm. So step 1, a minor transmission disturbance like a localized voltage dip. Step 2, the data center trips its internal protections to save the racks. Step 3, that's a simultaneous, near instantaneous disconnection of gigawatt scale load. Step 4, you get a sharp frequency change across the grid, which, if it's big enough, can cascade. This actually happened in July 2024 in Virginia in the US. A single line fault caused around 60 data centers to pull roughly 1,500 megawatts off the grid at once. It didn't cause a blackout, but it did cause severe instability. The regulatory response in Australia has been to draft some rules that formalise the threshold for these loads, lifting it from an informal 5 megawatts up to 30 megawatts in the national electricity rules, and requiring bigger data centers to actually ride through disturbances rather than drop completely offline. The whole capex cycle is resting on one assumption, that AI eventually delivers broad economic automation. Frontier Labs are earning $30 billion today. JP Morgan reckons that justifying a 10% return on the projected $2 trillion of AI investment through to 2030 needs around $650 billion in annual revenue out into forever. So that's $34 a month from every iPhone user in the world, or $180 a month from every Netflix subscriber. If the tech stalls and if human-level AI slips past the 10-year horizon, the venture money currently subsidizing the losses starts to dry up. That would mean a contraction in data center build-outs, leaving utilities with stranded transmission and overbuilt generation. Markets and operators are planning against these forecasts now, so the tail risk is across the board. To close it out, 3 pillars. Pillar 1, the base load is real. Agentic AI means a persistent structural inference load. We need to plan for multi-gigawatt interconnections in 2028 to 2030 and compressed delivery timelines. Pillar 2, we watch the leading indicators with 4 to track. So breakthroughs in continual learning, that's AI that can learn on the job. Improvements in reinforcement learning efficiency, this will shorten timelines. Agentic deployment scaling, currently it's only around 2% at scale, but when it moves into the double digits, that's going to be a different story. Whether power and chip limits force hard scaling ceilings. And then pillar 3, balance capturing the infrastructure build against the capacity overhang risk. To put it basically, we need to watch the gap between AI capex and revenue. To summarize it all, AI is no longer a downstream software phenomenon. It is the most significant vector of heavy industrial growth and grid security risk of the 21st century. Thanks for watching. If you found this interesting, please chuck it a like and even a subscribe. See you in the next one.